Let me record it. So again, the lab will be in about maybe 3 weeks. So the third one from now, maybe we'll have a lab, but exactly I'll find out this exactly with the coordinator, and then I'll let you know. Yeah, so about the exam also, I don't know if it is from your group or from other group, I don't know exactly, but there was a question also about the exam. I said that exam's supposed to be face-to-face, but then I was told by students that they have some other exams just online. So again, I need to find it out today. I'll find it out uh, with the office if we have face-to-face or online exam. So it doesn't depend on me. So I'll just let you know maybe later on about that. Any questions before we start? Okay, so then let's just continue what we started last time. I'll share the file with you. I also uploaded the lecture, so you can watch that lecture. So we'll talk about that one in details at some point, but maybe next class or today if we have time. But let's just continue with what we have started last time, and then we'll see if we have time. We'll also talk about the lecture I uploaded. Okay, so we talked about the mass and we talked about volume. If you remember, we discussed about volume and we talked about mass. Now let's just talk about density, because these three parameters characterize the matter in general. So density is mass over volume. So if you divide mass by volume, you will get density. And usually the unit for the density, it can be gram per milliliter or kilograms per metric cubes or gram per liter. So all this you can use as a unit, or gram per centimeter cube. So this is the same as gram per milliliter. For example, this is the same as gram per milliliter, because centimeter cube, as we discussed last time, cubic centimeter is the same as 1 milliliter, right? So you can just use interchangeably these units. But since this is, if you pay attention, this is solid and this is gases. And for gases, it's not really convenient to use gram per cubic centimeter. Sometimes it's used gram per liter or gram per milliliter and so on. So let's just compare what are densities of solid, liquids, and gases. And you can see here that solids are much more heavier than liquids and gases. Only exception is ice versus water. So you can see that ice is lighter than water. So the reason is that once water solidifies, the structure, because of particular structure of water and bonds between water molecules, it makes it a little bit lighter after it's solidified, because once it freezes, it keeps particular structure which is less dense than water. Okay, but everything else, if you pay attention, solids are heavier than liquids. So it means that for the same volume, if you compare, so the volume is that cubic centimeter for both, say for liquids and for solids. But say if you compare iron to acetone, right, it's like 10 times heavier, because yeah, there is a question.
Hello, doctor. It's Said. Yeah, I have a question. Is this exact number of densities is important for exam?
No, you don't need to remember all this number, of course. I don't remember myself. So if you need, if we need these numbers, you'll be given these numbers. But say you need to calculate something, you need to know how to calculate it. Say if you want to calculate density, knowing mass and volume, you should understand how to make it, how to calculate it. But of course, these numbers you don't need to remember. I don't remember myself. Only
Okay.
thing you need to know is that to understand that the solids are heavier than liquids and they are heavier than gases. Okay.
Okay, thank you.
Um, all right. So and if you look at here, so you can clearly see that solids are heavier than liquids. So let's just see how we can calculate, how can we use this information to calculate something. It says over here, calculation of density. Um, and so there's particular text over here that gold in bricks, bars, and coins has been a form of currency for centuries, right? In order to swindle people into paying for a brick of gold without actually investing in a brick of gold, people have considered filling their centers of hollow gold bricks with yeah. So they put some other material inside. Um, say if the gold was the currency, right? So if there is a brick of gold, some people would put, say, lead in the middle of this gold, making the basically cheating, basically doing the cheating. But you can easily find it out if you measure the density of, if you know the volume of that particular brick of gold and you know the mass of that gold, you can measure density. And if density doesn't coincide with the known density of gold, you can easily find out that this is kind of fake and it's not like really gold. So this is one way to find out if you have exactly the gold or it's something else. And for example, let's just do some calculations. And for example, you can use this approach to really find out the density of some kind of shape of the metal, or for example, gold is, since we are talking about the gold, and use this approach to find out if this is really gold or there's a fake, say, I don't know, brass or some copper in them and things like this. Please look at this slide. So we have rebar. So this is rebar. It's called rebar, and it's made. We don't know what is this made of. We have no idea. But what we know about this rebar is the mass. So we just measured this mass of this rebar on balances, and we found out that the mass of this rebar is 69.658 grams. Okay. And then what we did is that we measure the volume of this piece of metal. So how we measure the volume? It's very simple. Say you have a water, just water, right? And if you put this rebar in that water, or how the level of water changes gives you the volume of this rebar. For example, at the beginning, the initial volume of water was over here, right? Its initial one, it's 13.5 milliliters. So this is this one. Then once you put this rebar in there, you can measure the final volume over here, right? So the difference between these 2 points, for example, is the volume of this rebar. So how you can find this volume? Very easily. So you can just 22.4 milliliters minus 13.5 milliliters, it gives you 8.9 milliliters, right? Or it's the same thing as 8.9 cubic centimeters of volume. So right now, you know the volume of this rebar, right? And also you know the mass of this rebar over here, right? So you know the mass, you know the volume. So you can calculate density of this rebar. And once you calculate density, then you can compare this to the theoretical or known density for different metals. So for example, for this particular one, it was found that this is 7.8 gram per cubic centimeter. So if we go back and look at this table, 7.8, very close to 7.8 is iron, right? So for iron, it's 7.9 gram per cubic centimeter. So you can say that this rebar is made of iron, okay? This is iron. Do you guys understand how we can calculate the origin of the matter? Is it clear?
Yes,
Yes, doctor, it's clear.
Okay, so now let's just try to find out what is this metal over here. The same approach, you can do the same approach to find out what is this piece of metal here. I'll give you several minutes so you can calculate that.
I think 19.1.
19.2.
19.2. Okay, let's see. What did you do to calculate to find this 19.2?
I found the volume for the matter.
Final
Then
volume.
this one, the mass,
Yeah.
under the volume, so it will be 19.2.
Okay, so what is the unit for that, what you found?
Gram per
gram
centimeter.
per centimeter cube.
Yeah,
Milliliter.
gram per cubic centimeter or gram per milliliter, right? Let's see.
Yeah.
Yeah, so it says that answer is of 19 gram per cubic centimeter, so it's gonna be gold. If we go to this table, it says gold over here, so it's 19.3 gram per cubic centimeter. So it's close what you calculated. So this is how you can find out the origin of say metal. So it's quite very simple approach, but it gives you quite a nice result. Just a couple of questions here. For example, the first one: when elemental iron corrodes, it combines with oxygen and in the air to ultimately form the red-brown iron oxide, which we call rust. So how do you think when the iron is corroded and rusted, will the mass of that piece increase or decrease? How do you think? So imagine that you put a nail of iron outside for a long time and there was raining and then eventually this nail rusted, okay? How do you think the mass of that piece will be increased or decreased?
Increased.
Yeah, why it would be increased? That's true, it will be increased. Why?
Because it has its volume. It has the volume.
Well, volume will be changed, that's true, but why mass will be changed?
Because the rust will be added to the metal or the gold or whatever.
Yeah, so and what is this rust? So the before something is rusted, say before iron is rusted, it's just iron, right? And once it is rusted, then it combines with oxygen, and the mass of oxygen is added to the whole mass of that piece. So this is why the rusted piece of, say, iron will be increased in mass, because the mass of oxygen is added to it. So you make rust after combination of iron and oxygen. So this is why the mass is increased. So there are some other questions. You can just read this one and understand what is happening. Okay, let's just continue. Also, I want you can calculate all these things at home. For example, do you guys understand, right? Calculate these masses. So what is the mass of 6 cubic centimeter of mercury? So density is given over here, 13.6 around gram per cubic centimeter. So how you calculate it? You have density, you have mass. You just divide. You just divide. You multiply density by volume and you calculate the mass, right? Or if you know, or opposite. So if you have to calculate volumes and you are given mass and you know density, you just divide mass by density and you can calculate the volumes. So you can do it also at home. For example, here is a case when you need to understand, volumes, how much you need to deliver of medications. And it says here that deciliters and milliliters, how to convert these deciliters, milliliters. Okay. For example, we talked about this one. You remember we at the very beginning of our practical class, we discussed about how to convert deciliters, centimeters, millimeters, and so on, right? So it says over here that 1 deciliter is 0.1 liter, and 1 milliliter is 0.001 liter, right? So 1 deciliter is 0.1 liter times 1 milliliter over 0.001 liter, so which is 100 milliliters. So 1 deciliter is 100 milliliters. Okay, because of this conversion which is given here. This is a little bit early to do this, but let's just do it before we go to concentrations. Let's just look at this very simple example and you understand how we convert some amounts. For example, it's given that patient requires injection of 0.012 grams of painkiller, which is available as 15 milligram per milliliter solution. Okay, so the question is how many milliliters should be administered? So first of all, what is very important in general to answer questions like this, you need to bring all units to the same dimension. For example, what I mean by this is that you can see here that it says patient requires injection of 0.012 grams of painkiller, right? But the painkiller itself is given by 15 milligram per milliliter, right? So the patient needs 0.012 grams, but the painkiller is given in milligrams rather than grams. So what you need to do is that you need to convert either milligrams to grams or grams to milligrams. Whichever is okay, doesn't matter, because you need to bring both to the same dimension. For example, if you want to convert 0.012 grams to milliliters, milligrams. So how many milligrams would be this 0.012 grams? How many milligrams? What I should put here?
12 milligrams.
Yeah, so I should put 12 milligrams. Okay, so I should put 12 milligrams in here. So what does it mean? That patient needs 12 milligrams to be administered, right? And then it's easy to find out how many milliliters he needs to be given, because the painkiller comes in the amount of 15 milligrams per milliliter. So now I have a question. How do you think the patient needs less than 1 milliliter or more than 1 milliliter of
Less
painkiller?
0.8.
Yeah, definitely it needs
Yes.
like it needs less than 1 milliliter, because 1 milliliter already is 15 milligrams, right? So, but patient doesn't need this much, so it needs less. So if it needs less, it means that you need to deliver less milliliters, less than 1 milliliter. Yes, it will be about like 0.8 milliliters. So it makes sense. Once you get the answer like that, you need to think if it makes sense or not. Okay, and you need always to check your answer, otherwise it might be wrong. And don't forget to check it and think if it makes sense or not. This is very important. Yes, in this particular case, it means that you will get basically you can divide 0.012 by 0.015, and whatever you
0.8.
yeah, you will get 0.8 milliliters of painkiller. Okay, I'll leave it for.
Excuse me.
Say that again. Yeah.
Can you go to the previous page? I have a question.
Here.
Yeah, in the second one, B.
Yeah, here.
B, yeah. Should you convert? No, the second B.
This one.
Yes. The 125 milliliters, should you convert it to liters or keep it?
Okay, so if you have density in liter, right? So it says that density is 3.16 gram per liter, but you have here milliliters. So you need to convert this one to liters in order to have the same unit as here. Okay. Yeah, you need to convert it to liters.
Yeah, okay, but in the ones above, like for example, in the first B, you just put 25 centimeter cube because the milliliters is equals to the cubic centimeter,
Right,
right?
right. So this is basically the same as cubic centimeter. So you don't need to make anything with this. So basically the same. But here definitely you need to, if you don't do so, then your answer will be 1,000 times different from the real answer. So it's very important to look at units. Otherwise, the answer might be erroneous. Okay, so it's very important to keep these units at the same dimensions. Otherwise, the outcome might be very different. So and it really can hurt. So for example, if you want to administrate some drugs and you don't calculate the right, so you will have really problem with that, right? So you cannot give patient more than he needs or less than he needs. So it's very important to keep these units very, very strictly aligned. Okay. The same thing here. So if you don't convert this one, so you will have 1,000 times different answer, right? And then completely wrong outcome. And this is about patient. So you cannot like risk the life of the patient. So it's important. So you might think that, we don't need all these calculations and, but this is the example when you really need to understand how to convert units, how to convert amounts, how to calculate it, and so on and so on. So I think that it's really important. I'll give you this example for yourself so you can practice at home. It's basically the same approach what we just talked here about. Just the difference might be that this is micrograms. So micrograms is 1,000 times less than milligrams. So again, you need to recalculate these units and so on and so on. So it says everything here. So what you need to do. All right, so let's just move to really chemistry, which is basically basement, how you calculate all these concentrations and everything. And let's just discuss about atomic mass and then mole, which is very, very important. Molar mass and mole and so on, which this is very important. We need to understand this one very well. One thing is that in general it's important for your knowledge, but again we will have some exams based on this. Also basically the laboratory will be based on knowledge you will get from here. Okay, so what is given here, I don't want you to confuse, but in general, the carbon is a very important element. I mean, all elements are important, but carbon is used very often in many cases. And you know that this is basically, once we go to organic chemistry, it's like backbone of organic chemistry. And but here it's also used as a reference to compare atomic masses of all other elements, to compare it to the mass of carbon. And this is the average mass of carbon. It says over here that in the nature we have two different carbons. One is carbon 13, the other one is carbon 12. So the differences between these is that carbon 13 has one additional neutron. Okay, so it's a little bit heavier than carbon 12. All right. So, but the abundance of carbon 12 is much, much more. It's 98.9% versus carbon 13, which is just 1.1%. Okay. Overall, this is what is carbon kind of made of. And if you look here, eventually the mass of carbon is calculated based on both allotropies of both carbons. Okay. Now let's just see how we need to characterize mass of elements, because you understand that one atom is very, very, very small. Last time I showed you that mass of atom is incredibly small, and size is also very small. So it's basically impossible to measure the mass and manipulate with the mass of only one atom. Okay, it's impossible. It's the same thing if you go to the market and you ask a seller to give you, say, 1 million of grains of rice, right? Because you don't buy rice one by one, right? You don't buy 1 grain by 1 grain and so on. You just buy, for example, 1 kilo of rice, and nobody counts rice by grains because it's like absolutely inconvenient. And it's impossible to deal with this, because nobody can give you, say, if you ask the seller to give you 1 million of grains of rice, this doesn't make sense at all, right? Because you cannot just count 1 million, it will take forever. So the same thing, kind of the same thing is here in terms of elements and molecules and atoms, okay? Because nobody wants to count just one single atom. Because of that, there is a particular tool, let's say like that, to identify the mass of elements, of mass of atoms of elements. And that one is designated as mole. Okay. So what is this mole? So this mole is the amount of substance that contains as many elementary entities, atoms, molecules, or other particles as there are atoms in exactly 12 grams of carbon-12 isotope. So in other words, what is happening here is that 12 grams of carbon-12. So I told you, right? Carbon might be 12 and carbon 13. So carbon 12 is taken 12 grams, okay? And it was found out that carbon 12 grams contains particular amount of carbon atoms. And that particular amount of carbon atoms is the same as 6.022 times 10 in power 23. Okay, so and this number was called Avogadro's number. All right, so 12 grams of carbon is it contains this amount of carbon atoms, and this amount of carbon atoms is considered as 1 mole of carbon atoms. Okay, now what is happening with other elements? So with other elements is happening the same thing. If you take any element with this amount, you can say that you have 1 mole of that element. Okay, so anything you take this amount, say if you take this amount of cell phones, right, which is huge number. I don't know if there is any numbers. No, it's impossible, right? But just imagine if you take this number of cell phones, you can say that you have 1 mole of cell phones. Okay, so again, any element taken in this amount, in this number, it means that it's taken as a 1 mole of that element. All right, and the reference for that again is 12 grams of carbon. Is it clear? Any questions here?
Yes.
Clear.
Okay, so it says over here that we have seen that 1 mole of carbon 12 atoms has a mass of exactly 12 grams and contains 6.022 times 10 in power 23 atoms. So this mass of carbon 12 is its molar mass. So molar mass of carbon 12 is 12 grams. Now I have a question for you. For example, if we say that hydrogen is 12 times lighter, I'm sorry about this writing, lighter than carbon. Okay, than carbon. So what's gonna be the mass of 1 mole of hydrogen? How do you think? Okay, again, we know
Avogadro's
that
number divided by 12.
well, if you divide Avogadro's number by 12, it will be huge number. Okay, so if you divide Avogadro's number by 12, it's going to be 0.5 times 10 in power 23. So it's absolutely huge number. So you cannot have such a heavy element. Again, so the question is that I'm saying that hydrogen in general is 12 times lighter than carbon. So what's going to be the mass of 1? Okay, yeah, so what's going to be the mass of 1 mole of hydrogen? So I have a question. So what is the mass of 1 mole of carbon?
12 grams.
Yeah, exactly. It's 12 grams, right? So now I'm saying that hydrogen is 12 times lighter than carbon. So what's going to be the mass of 1 mole of hydrogen?
One gram.
Say it
1
again?
gram.
So it's the same as Avogadro's number
Less.
times 1.
No, just
That's less than 12 grams.
It's 1 gram.
yeah, it's going to be 1 gram. It's going to be 1 gram. So 1 mole of hydrogen's mass is going to be 1 gram. Okay, so the same thing. Look, so 1 mole of carbon is 12 grams, right? So I'm saying that hydrogen is 12 times lighter. So 1 mole of hydrogen is going to be 1 gram. because it's 12 times lighter than carbon, okay? So it's gonna be 1 gram. So now I have a question, another question. Say how many atoms of hydrogen is gonna be in 1 mole of hydrogen? So you have 1 mole of hydrogen. I have less than 1 minute, but please come back after the Zoom is off. I have 1 mole of hydrogen. How many atoms of hydrogen I will have in this 1 mole of hydrogen? How do you think?
1 mole times the Avogadro's number.
Yes, exactly. So it's going to be just Avogadro's number, which is 6.022 times 10 in power 23. Say if I have 2 moles of hydrogen, how many atoms of hydrogen I will have?
2.
Times 2. The Avogadro's number times
Yes,
2.
Avogadro's number times 2. This is the amount I'll have in 2 moles of hydrogen. Okay, so what's going to be the mass of 2 moles of hydrogen?